slides. First, in this slide, C sub P represents the price when we try to sell a single item to the customer. Okay, please make sure. And then one more. In the example, I mentioned last class. Here, large D is a discrete random variable, not a continuous random variable. Okay, so please make sure, and then please change this typo. And last class, I explained about use spender problem and how to formulate maximizing profit problem for a use spender problem. And then actually, as long as we can calculate such expectation means expectation of minimum of y and d, and expectation of maximum of 0 and y minus d. Okay, then we can calculate expected profit for a given y, and we assume that the distribution of d is known, right? And then today we are going to talk about how to find optimal value for y that maximizes this expected profit function for general case. Actually, you can use some formula, very simple. Result is very simple, and you can just use it, but I'm pretty sure you need to know why we can use this formula in this structure. Okay, so I'd like to go over step by step how to derive the formula. Okay, and then each step we can see some techniques when we try to calculate some integral and the summation and the probability. This is very important techniques and basic techniques. Okay, so let's start with easier case, continuous demand. Okay. So if this random variable D is a continuous random variable, then this expected profit of function of y can be rewritten by C sub P minus C sub V. Actually, this times expected value of minimum of y and large D minus CV minus CS times expected value of maximum of 0 and y minus D. Okay. And this expectation for continuous random variable D, we can rewrite this expectation using integral C sub P minus C sub V times. So we assume that demand cannot be negative value. Okay, and in practice it is true, right? So we can think about integral x is 0 to infinite, right? And this is about calculating expected value of a function of a random variable D, right? You can check the slide, probability review slide, how to calculate it. So y, minimum of y and x and f of x dx. Here f of x is what? What is f of x? PDF, probability density function of which random variable? D, right? This small f of x p d f of d. And since we consider a continuous random variable d, we need to consider integral rather than summation to calculate this expectation. Okay? And similarly, this part, c sub v minus c sub s times integral x equals 0 to infinite y minus x, maximum of y minus x and 0 times f of x dx. Okay? And then we can rewrite this part. Okay. We can partition the range of x into two different sub-ranges. How can you partition to calculate this integral? 0 to y, then this value might be x, right? So x is 0 to y, and in this case, this function return x times f of x dx, right? And then rest of them y to infinite. In this range, this function returns y f of x dx, right? How about this? How about this part? 0 to y. Then this function returns y minus x. And how about y to infinite? 0, because this function returns value 0. Okay, when we integrate 0 from some range, from some to another value, that might be 0. Okay. Question so far? No? And then we need to transform this part again. This part. Okay. Actually, y can be considered as a constant to calculate this integral, right? So we can move y outside the integral. So this might be y times integral y to infinite f of x dx. And also, we want to change this part for integral from x is from 0 to infinite. So we can manipulate it. Actually, this one represent probability that d, large d, right? Large d greater than or less than? Greater than equal to y, right? And this probability can be rewritten by 1 minus probability d is less than y. So we can rewrite this part 1 minus integral x from 0 to y f of x dx. Okay? This part, actually y is independent. We can consider y as a constant for this integral. So y times 0 to y f of x dx minus 0 to y x times f of x dx. Okay. Okay. And for your convenience, we are going to use different letter. Instead of C sub p minus C sub v, we are going to use A. Okay. To simplify the equation. Okay. So let's say A is Cp minus Cv. B is Cv minus Cs. Okay. This one. Okay. Then, okay, let's consider this part. First one, and this part, second one, okay, and this part, third one, and this part, the first one. And then we can rearrange each part, okay? We can get, when we sum the first part and the second part, this part and this part, okay? Actually, integral parts are the same. We can think about the coefficients in front of the integral. Okay? Then, this first part plus second part gives us A plus B times the same integrals 0 to infinite, y x times f of x dx. Okay. And then this integral part and this integral part, they are the same, right? Range 0 to y, okay, for the function f of x, right? So from 3 and 4, this part and this part, we can get minus A plus B times y, right? Times 0 to y f of x dx. Okay. And then rest of them, this part, right? Minus plus ay. Okay. Can you do it? We can manipulate the range of the integral. Okay. And then rewrite with some coefficients. Okay. So we can rewrite this. A plus B 0 to y x times f of x dx minus A plus B y times 0 to y f of x dx plus ay. Okay, and then I'm going to erase rest of them. Okay. So now, even though we derive a formula instead of p of y, still we have integral, right? Integral. But our ultimate goal is finding y that maximizes this p of y. Okay, ultimate goal. We want to find y. Let's say y star, such that maximize p of y. Okay, that means at y star, this value is maximized. How can you find such y? Differentiate. Okay, take the first order derivative of the function and make it 0. Then we can find local minimum or local maximum. We call them critical points or saddle points, right? Critical points. And then we need to check one more. Second derivative of the function at the point is greater than 0, less than 0, or equals 0. Right? So let's do it. Before we do such things, we need to know very important and the basic concept called fundamental theorem of calculus. Okay. If we consider such integral 0 to y h of x dx, we call this large h of y, and then take the first derivative of the large h of y, then that might be the small h of y. Okay. So we want to take the first order derivative for the function p of y. So the p of y over dy. Then how about this part? How can you change? A plus b times y times f of y. Here h of small h of x is x times f of x, right? So from fundamental theorem of calculus, we can derive this. Okay? And then how about this part? We need to consider chain rule, right? Function of y and the function of y. Okay? Minus a plus b. When we take a derivative for y, regarding y, then 1, right? 0 to y f of x dx plus, we can take a derivative for the later one, then y times f of y plus the constant a. Okay? We need to make this 0 and then solve for what? Solve for y. We want to find y. We want to find y that makes this part 0, right? So when you see this left-hand side of the equation, this part and this part, they are cancelled out. Okay. And how about this part? Can we rewrite this integral with CDF of random variable t? Can you do it? This one represents probability that d, large D is less than or equal to y, right? That means if large f of y represents CDF, cumulative distribution function of random variable t, then this one can be rewritten by a plus b large f of y plus a equals 0. In other words, as long as we can find y equals large F inverse a over a plus b, okay, then this y can be critical point of the function, right? Any questions so far? Question? Large f of x. We don't care any this part. This part can be any variable. So we know that as long as we can find, so A and B, they are given. Okay? In other words, CP, CV, CS, they are given numbers. Okay? As long as we know CP, C sub V, C sub S, then we know A, B, right? And then, as long as we know the distribution function of D, then large F is known. Okay? And then we can find such y. Okay? One more step. Y can be local minimum, local maximum, and saddle point. So we need to figure out the second derivative of the function p of y. Okay, solution of this equation, y equals f inverse a over a plus b. Okay, and then we need to figure out whether this point is a local minimum or local maximum or saddle point. So the second derivative of p of y, then this might be negative a plus b times PDF of D, right? When we differentiate the CDF, then we can get PDF, right? This, and the constant 0. Okay, let me see. Here, A plus B is CP minus CS. And usually, the salvage price might be less than selling price. Otherwise, we don't have to sell this item to the customer, right? So, this part, positive. How about this part? positive, right? PDF values should be greater than or equal to 0. Definition of the PDF, greater than 0. For any y, this one might be less than or equal to 0. So what can you know? What do we know about this result? As long as we can find such y, okay, then P of y might be global or local maximum. Global. For any y, this is true, right? Therefore, this y a over a plus b is the optimal policy regarding our formulation. Okay. Any question? So as a result, as long as you can understand this formula, then you can use it, right? You can use it. But still, there are many things to get such result. Okay. Sometimes you can use it to derive different concepts, different theorems, different results. Okay. Very important. Any question? So if you don't have any question, then I'm going to explain about how to derive, how to find optimal policy for discrete random variable t. Okay? More complicated. Okay? So when we try to calculate expectation of the discrete random variable, then you need to come up with summation instead of integral, right? But to derive such case, we need two assumptions. First one, assumptions. First one, these candidate values of demand d0 to the, let's say, large n, it can be infinite. Okay, 0, 1, 2, 3, 4, 5, and then up to infinite. Okay, actually in practice demand occurs with this discretized value, right? This week I can sell the car like 10 cars. Next week, 12 cars, but we cannot define 12.5 cars, right? Because usually this demand occurs with discretized value, right? And we are going to consider increasingly ordered values this large D can take. Okay? Increasingly ordered. And then second assumption is this optimal policy y should be 1 of di, I 0 to large n. Okay. Demand occurs with the discretized values, and then we are going to select one of the values as the optimal policy, okay, to maximize the profit in the Nussbender problem structure. Okay. So as we did before, we are going to use A instead of C sub P minus C sub V, and B instead of C sub V minus C sub S. Okay? Then this P of Y can be rewritten by A times expected value of minimum of Y and large D minus B times expected value of maximum of 0 and Y minus D. Okay? And we want to calculate such profit function for a certain value Y for discretized discrete random variable T. Okay? First, we want to calculate this P of S. So here is the idea. We want to figure out the relationship between P of DI and P of DI plus 1, T of Dn and T of Dn plus 1. Okay? So if we calculate P of Dn plus 1, this might be, by definition of the expected value of the function of D, discrete random variable D, this might be A times sigma x 0 to infinite Dn plus 1 cos Y equals Dn plus 1. Okay? Y is at Dn plus 1. Minimum of Dn plus 1 and x and P of x. Here, sorry, f of x. Let's say this f of x is probably the best function for D. In other words, probability that large D equals Dx. Okay? Minus B times summation x is 0 to infinite maximum 0 and y minus x f of x. Okay? And this part can be partitioned into summation x is 0 to Dn. This function returns x, right? X of f of x plus x is from Dn plus 1 to infinite. This one returns Dn plus 1 f of x. How about this part? From x equals 0 to y, this one returns y minus x, otherwise 0. So this part, summation x is 0 to infinite, 0 to y minus x f of x. Okay? And here is very important technique. We would like to figure out the relationship between P of Dn and P of Dn plus 1. So we are going to change these summations. Any question? Okay? So here, here, sorry, Dn plus 1. Okay. Here, Dn. Yes. Right? As long as this x is less than dn plus 1, return x. Otherwise, dn plus 1. Okay? And then we are going to manipulate. So in the continuous case, we consider the same range for the integrals, right? In this case, same range is for sigma, and then we want to find the relationship between p of dn and p of dn plus 1. So we can manipulate this part and this part, okay? So this one, a plus a times summation x is 0 to dn x times f of x, what we have. And then here, dn plus 1 can be rewritten by dn plus 1 minus dn, right? They are the same. Okay? So this part, summation x equals dn plus 1 to infinite dn f of x. Please be careful about the subscript. That's the main idea of this a times, okay? A times plus a times summation x equals dn plus 1 to infinite dn plus 1 minus dn f of x. Then this, when we sum this part and this part, we can get this, right? Similarly, this part minus p, instead of dn plus 1 minus x, we can use dn minus x plus dn plus 1 minus dn. Okay, then we can get the same result, right? So b times summation x is from 0 to dn plus 1 dn minus x f of x minus b times summation x is 0 to dn plus 1 dn plus 1 minus dn times f of x. Okay. Okay. First, we can decompose the range of the summation, and then second, we described this equation to figure out the relationship between p of dn and the p of dn plus 1. The thing is, when we consider this part and let's say this one, part 1, part 2, part 3, part 4, part 5, then we can come up with the result. So this one might be the same as p of dn plus dn plus 1 minus dn. So okay, this part, actually when we sum the first part and second part and the fourth part, okay, we can put dn instead of dn plus 1, then we can get the same result. Okay? And then rest of them, dn plus 1 minus dn times times, okay, here, okay, a times summation x is dn plus 1 to infinite f of x, right? Right? This third part can be here, right? The same. Right? But we can rewrite this 1 minus large f of dn. Okay. This one represents probability that large D is greater than equal to dn plus 1. So 1 minus large D, probability that large D less than or equal to dn. So this, okay. So 1 minus large f of dn, and similarly this last part can be minus b times large f of dn. Sorry, here it might be dn. Okay. Otherwise 0, right? dn. Okay. So here, is this positive value or a negative value? dn plus 1 minus dn, positive or 0, right? Because the first assumption, increasingly ordered positive value. That means as long as this one is positive, then when we increase this y, this p of y also increases. In the other way around, if this one is negative, then p of y decreases. Okay? So we can come up with such results. So if this a times 1 minus large f means CDF of D, okay, f of dn minus b times large f of dn is positive, then p of dn plus 1 might be greater than or equal to p of dn. Okay? Otherwise, that means this part is negative value. Then p of dn plus 1 less than or equal to less than p of dn. Okay? And then based on this result, we can see that as long as we can find if we can find dn plus 1 such that f of dn as long as we can find such a Tn plus 1, then this y star can be the same as Tn plus 1 in this case. Okay? In other words, after Tn plus 1, this function decreases. This function increases until Dn. Because Dn, they are increasingly ordered. It always depends on the Dn and Dn plus 1. And the thing is, this function, profit function, has like if we consider continuous function, then this one is kind of convex function for all Dn. So increasing and at some point decreasing, it starts with the decreasing tendency, then decreasing forever. Okay? Then the point is here. Okay? That means as long as we can find smallest Dn satisfying this inequality, then that might be the optimal policy.